Hi, good morning and good afternoon, everyone. This is Raj Dua, Product Manager at MSC Software, and I'm going to talk about what's new in MSC Nastran 2018.0. Okay, so for today's topics, we're going to talk about general licensing updates, and then next we'll move on to our updates for linear dynamics. And then I'll pass it on to Farnaz for our enhancements in nonlinear and explicit nonlinear and HPC. Okay, so for our first topic, we're going to talk about some of the enhancements that we made in our licensing. So for the first time in MSC Nastran, we're supporting IPv6, and we're compliant with IPv6. For compliance with IPv6, we had to upgrade to a new server version for licensing, and that's listed on here, FlexLM 11.13 server version, and that is required for the license features. For security purposes, we have removed several security issues that were associated with ENCODE and ACTRAN. In particular, we've eliminated libraries that were not supported, and we've also updated some older Python versions. Okay, next we're going to talk about our enhancements in linear dynamics, our linear solver. Some of the topics I want to touch on are the general frequency spatial dependency, rotor dynamics, a new feature that we call multiple mask configurations, and a new FemCheck command. So let's start with our general frequency and spatial dependency. So for applications such as NVH, noise, vibration, and harshness, a lot of engineers are moving towards using lightweight materials, which are also good for noise abatement and vibration in all NVH applications. Such materials are laminated metals or NVH laminates. These are, for example, too-thin steel layers which sandwich a viscoelastic material in between, or they could also be layered in short fiber reinforced plastic composites. To capture the true behavior of these materials for NVH applications, it is necessary that the stiffness and damping properties of these materials are frequency and spatially dependent. For this new version of MSC Nastran, in MSC Nastran 2018.0, we've added the capability of defining your material properties to be frequency and spatially dependent. And these properties can be stiffness or damping properties. In the older versions of MSC Nastran, the damping properties were proportional to your stiffness, were dependent on your stiffness matrix. In this new version of MSC Nastran, we've removed that restriction. Moreover, in additional applications, the short fiber reinforced plastics, depending on the way the fiber orientation is distributed, the properties can vary from location to location. So it is important to be able to model these spatially dependent properties. So now in version 2018.0, now we can account for both frequency dependent and anisotropic damping. In another application, a lot of manufacturers are moving towards using composite materials. Draping of composite materials onto complex shapes necessitates defining a PCOM property entry per element to accurately define ply orientation and thickness. What that means is generally for an entire part you'll define a PCOM property entry, but draping of composites on these parts can change the thickness or orientation at certain locations of this part. In that case, in order to not having to define PCOM property entry per element, now we've introduced a new PDIST-B entry, so you can modify the thickness and orientation properties for certain elements in the part and not change the entire PCOM property for the part group. So for the user interface, we've For the case control, we have a MFREQ command, MFREQ entry for specifying master solution frequencies, and we'll talk about that a little bit more in upcoming slides, but that is for modal analysis purposes where you don't have to find your stiffness and damping properties at each frequency. Instead, you can just specify some master frequencies, and we'll give you some recommendations on how to define that. For our bulk data, we've defined new material card entries, MAT1F, MAT2F, MAT8F, and so on. These are for isotropic, anisotropic, and orthotropic material properties, which are similar to our existing MAT1, MAT2, MAT8, with the exception that now you can define frequency dependency in these material cards. For composite and fastener properties, you could also define frequency-dependent damping coefficients, and that's done by PCOMP-FQ and PFAST-T entries. We've introduced a new parameter, nominal frequency, to select for modal analysis. You can select a nominal frequency other than 0 Hertz for computing mode shapes. And also, we understand for all dynamic analysis, residual vectors are very important. So we've enhanced the residual vectors for viscous and structural damping as well. Here's an example of a comparison between a solution 108 and a solution 111 analysis. In this case, we've done solution 111 analysis with the nominal frequency of 143 Hertz. And this is for a laminated metal, 2 thin steel sheets, which sandwich a viscoelastic polymer in between. And as you can notice, the solution 108 is represented by the blue curve, which is not really visible but because it's overlaid by the green curve. And solution 108 is for 1400 forcing frequencies, whereas for solution 111 we've only picked 11 master frequencies, and we can see that the frequency response is almost identical. And the trade-off is great because the computation time is much lower. Okay. So a little bit more about the MFREQ case control capability. It makes it possible to define master frequencies at which you can compute your frequency-dependent stiffness matrix rather than at each frequency. At all the intermediate frequencies between the 2 subsequent master frequencies, the stiffness matrix is calculated by linear or logarithmic interpolation. We're also mentioning that only displacement, velocity, and acceleration results are available for those. Our recommendation for MFREQ selection is that for the 2 subsequent MFREQ master frequencies that you select, the change in stiffness and damping properties should be less than 10%. Okay, here's some other results, you can see the blue curve is without MFREQ, and then the red dotted curve, which is right on top of it, is with MFREQ, and you can see all the peaks are captured and the response is very identical, and the little gray curve there shows the error percentage, and we can notice that a difference, the maximum difference that we notice is less than 4%, which is trivial, but the computational time is reduced by 33%. In this case, we picked 20 master frequencies out of 100. So here's where we're showing an example of the benefits of defining your properties with frequency and spatial dependency. In this example, we're using a car roof beam, and on the right-hand side figure, you can see where the location of that beam is. It's kind of an important location because it holds the entire roof of the car and other important features. So for this example, we're doing a 3-point bending test, and on the left-hand side, you can see our model where we've constrained the 2 ends of the beam, and then we're applying a load right in the middle of the beam. And we're going to post-process our Z displacements in node 602, which is represented by the red dot. For this model, we have roughly 12,500 first-order shell elements, and we're doing a direct frequency response analysis over 100 frequencies distributed over from 10 to 300 hertz range. For the material of this beam, we picked short fiber reinforced plastic with 30% fiberglass in volume. This is our MSC Digimat user interface. Digimat is a MSC-owned program, and you can use it to define your material models. For this example, we picked, as I mentioned earlier, a composite polymer with fiberglass, and it shows you your stress and strain curve. You can import, in Digimat, you can import your solution 108 or 111 Nastran input file, and you can define, it will upload the material, and you can define your material and then output your Nastran bulk data file that's ready for solve. So here we're showing the final results. We ran 3 different cases. The red curve that you see is for the frequency response by neglecting frequency and spatial dependency. As you can notice, this misses some of the peaks and could result in over-designing. However, for the green curve, we've accounted for frequency dependency, but we ignore spatial dependency of the fibers. In that case, you can notice the response is much better. However, it's still not as accurate as it would be if we do it with Nastran 2018.0 by including frequency and spatial dependency. Next, we're going to talk about some of our enhancements in rotor dynamics. If you're a user of rotor dynamic capabilities in Nastran, you may already know that we've consistently updated our rotor dynamics capabilities. In 2017, we introduced support for 3D rotors. One thing we noticed in our previous versions of Nastran is that depending on your rotor speed, your mode shapes may switch, and therefore for this version of 2018.0, we have added mode tracking capability and our enhancer algorithms. Our mode tracking algorithms are based on orthogonality of left and right eigenvectors, but we can also do it numerically based on first and second derivative continuity. We've also improved output for a complex eigenvalue analysis, in which case we correctly identified rotor world type for each rotor in the model for both synchronous and asynchronous analysis. We've included cross-coupling terms for an enhanced P-Bush 2D entry, which can be used for bearing analysis and such. We've also added SE dam handling for correct modal damping in super elements. And finally, in this version of Nastran, MSC Nastran, we support rotors in part super elements. We'll talk about that a little bit more. We allow definition of 1 or more rotors in part super elements, and they're supported in both single and multi-level part super elements. So this is just an example output where we're showing how well MSC Nastran can track the modes. Some of the limitations of eigenvector-based mode tracking, they can only use with Hess option, and it's for analysis in fixed reference frame only. So rotors in part super elements. Rotors can now be defined in single and multi-level part super elements. To define rotors in part super elements, just like any other super element, you'll put all your rotor definition under begin super section of the model. All the corresponding spin entries and R gyro entries are defined in main bulk data section. For part super elements, you can, just like any other part super elements, you can mirror and repeat and copy your super element for another location as well, as shown in that the figure in the bottom for the engines. Okay. Next, we will talk about what we call our multi-mass configurations. Initially, when we started this effort, this was the application that we were thinking of was a typical aerospace application where you may have to run an analysis with multiple mass configurations. This could be because of different structural mass, different payloads, multiple fuel configurations, or other environmental conditions. To account for all these, in the previous versions of MSC Nastran, you had to rerun or you had to find workarounds to do it. But in this version, we've added capability for constructing and analyzing additional math cases for all standard linear, nonlinear, and optimization solution sequences. They're similar to loads and boundary conditions. We can add math increments in addition to the base math in the bulk data sections. So all of our solution sequences are supported, including solution 400. One comment on solution 200, optimization is supported, but only with the base mass quantity. Next, we'll talk about our topology optimization. We've added capability of shell stress constraints. So in this new version of MSC Nastran, we allow users to have a von Mises stress constraint at the center of the element for your design optimization task. The benefit is this eliminates the guessing of right fractional mass constraint in your classic minimization tasks. We're showing an example of the input for the top bar entry, and you can notice in the very last row, the stress ST limit is where you define your von Mises stress limit for your design constraint. So this is an example, the classic example of a clip on the left-hand side and the optimized shape on the right-hand side using our stress constraint for shell topology. In this case, as you can notice, the optimized shape is not symmetrical, and that is because the loading and boundary conditions that we defined for our initial part were not symmetrical. So once again, for our shell topometry optimization, you can also do the same thing. You can apply a von Mises stress constraint at element center, similar to the shell topology, and similar to the top bar entry and the top bar entry, you can also define a stress limit in the last, as shown in the last row. Next, we'll talk about a new FEM model checking feature. We've added a FEM check command in MSC Nastran 2018.0. This allows you to apply many options to FEM check, for example, RB3, deload, frequency, SDAMP, or T-step, or you can do all. This FEM check command checks models at the start of the run. For example, if you pick RB3 only, then it will check for RB3 unconnected grid planes. For other options, it can check and validate solution 108 or 111 frequency response and solution 109 or 112 transient response case control. And all the capabilities are listed on the slide and can also be found in a quick reference guide. Okay, next I'm going to pass it on to Farnaz to talk about implicit nonlinear. Thank you.
Thank you, Raj. Hello, everyone. My name is Farnaz Jadbabi, and I'm one of the product marketing managers at MSA Software working with Nastran and Mark. Thank you for joining us today. I'm going to start talking about our implicit nonlinear dynamic solutions, a little bit about the modules and some of the output enhancements that have been added to MSC Nastran 2018. So we'll start with the external super elements in solution 400. The idea of having the external super elements is to simplify the model you're working with when you have a very complicated structure, and it would be inconvenient to have a lot of like disk usage and stuff like that. So when using these super elements, we have allowed and extended the capability to include them in Solve 400. So here you can see how it was done in the older versions, in version 2017. So we could create the external super element using a two-step method in multiple solutions, including solution 101, 103 through 112. And the step one was to create the reduced matrices, such as stiffness mass matrix, and also include the OTM data block for output transformation matrix. And then the next step was to recover the stress and the other values that you want and the components and get the data recovery. Now, in the version 2018, we have added more capabilities to the OTMs. So in the older versions, you could only get the stresses, forces, and displacements and SPC forces, but in the new version, in the 2018, as you can see, we have added more. We have also extended the capability to be included in solution 400, and so this is still, you can do a two-step method, where in the first method, you create the super elements and generate it, and then the second, do the assembly, and then in the second step, you do the data recovery. We have also added more items for the OTMs, where it supports the pre-stress stiffness and in the data recovery, and also the metadata. So if the two-step is not sufficient and you want to have more control over the data recovery process, we also have added a three-step method for the external super element generation. So it will have the super element generation, the assembly, and the data recovery. So those are the three steps. So can you go to the slide before? Yes. So here, as you can see, we have added this also in Solution 101. This was available in 101 through 112, but we've added it to the 400, where you have three steps. So again, the first step is the super element generation. Second step will be the assembly modeling, and the third would be the data recovery. So the first step is the same as before, and then you create the external SCs, but in the second step, you can use the Solution 400 nonlinear chaining, the perturbation, or any other type of multi-physics analysis. And the third step, you go to the data recovery. And the data recovery in this case is more broad in comparison to the previous two-step method, as you can have support over all the items that Nastran covers. So we can see the user interface here. Before, we had the EXTDROUT command, which was a parameter, but now we have added a new case control command. So we are replacing the parameters with the new case control entry for the EXTDROUT to attach the boundary matrices from the step 1. So that's why we specify this case control command. We have also added the EXTDRIN case control command to replace the other parameters that you can see here. And these can be used in Solution 101 through 112 and Solve 400. Additionally, we have added the capability to do the data recovery for the OP4. Before, we used to only have the XDB, DMIG, and OP2, but now we support data recovery in the OP4. So now I'm going to talk about our new automatic contact generation feature. This is mostly designed for for ease of use, to provide ease of use to you guys. And this release, we include the automatic contact generation. It makes it much easier for users to set up the contact data. As you can see, for several of your structures in the modern industries, the structures like planes and automobiles and so on are becoming more and more complicated with many parts. And these parts can come from different suppliers, different departments, or different people. So it's hard to manage them, and creating the contact can get very cumbersome at times. So using this automatic contact generation feature, one can quickly set up the automatically set up the contact bodies. And this will allow you to study the model. And for the more complicated models, you can use the HCG file that is created. This file consists of contact bodies, contact pairs, contact parameters, and this can be easily read into a preprocessor for further studies and advancements of the contact analysis. Or you can also edit this file in a text editor and use it as an include to rerun the analysis, or use it in another analysis. So this feature is supported for all contact types, for permanent glue contact, general glue, as well as touching, with both node to segment and segment to segment. So here you could see the engine gasket model. So we also use the, as you can see, it's a complicated part with several sections. We can use the B contact entry. So this is the entry that allows you to activate the automatic contact generation. For example, here we say B contact auto. That tells the solver to start creating the contact. And for G glue stands for general glue in this case. So you can see how it created several contact bodies for us, generated 8 contact bodies and 14 contact pairs. So the user interface, how does that work? It's very easy. You have a few case control entries. So even if you don't have a pre or post processor, you can use it in a text editor. You add B contact auto, and C type stands for the contact type. Again, as I said, it covers all contact types for permanent glue, general glue, and other types. And then we have the BC auto P bulk data entry section. This allows you to specify the parameters for the automatic contact generation. There are several options available to the user. For example, you can specify the ESET to specify the contact regions, or you can specify seed ESET or seed GSET. So for ESET is the default where all the elements that are in the set 1 entry that's referred with the ESET will be included in the contact bodies and in contact analysis, contact generation. Now, if you use the seed ESET, you can use an element as a seed element, and then the rest of the elements that are connected to that element will grow, and those elements will be connected and included in your contact region. Similarly, the seed GSET allows you to pick a grid, and then all the elements that are connected to that grid using the element connectivity will be included. The prop set allows you to define a set of properties, and all the elements that are called for that property will be included. Here we can see an example that I've included, I have shown. So BC Auto P, you see that we have an option for the friction type in case you're using the touching contact. Here we are using the seed ESET 1. You can see it's using elements 11, 201, and 36. This means that only contact bodies that have those elements will be included. So body 1 for element 11, body 2, and then body 3. So elements on body 4 are not included. That being said, if we had not defined the seed ESET and we have just set the ESET, all the elements in the model would have been included. So next I'm going to talk about another enhancement that we have added to Nastran 2018. That's for our GPFORCE output with contact forces and also advanced nonlinear elements. So before, we did not include the contact force separately in the GPFORCE output table. If you had used permanent glue contact, because they use MPCs internally, then you could have seen this under the force for MPC. And if you also had MPCs in your model, then it would have been a mix of the MPC forces and the contact forces. But for general glue, this was not available, so the GPFORCE output was not balanced. And also, the advanced nonlinear elements were not fully supported for the GPFORCE output for some nonlinear static analysis or for linear static analysis. Now, what we have done in the new version is added all of these. So you would see a separate entry for your contact forces. Whether you have touching contact, you'll see the friction force due to the friction. This is included in your GPFORCE output table, as I will show you in the next slide. And also, you can see that we have added the advanced nonlinear elements for the nonlinear analysis, for linear analysis, for multidiscipline analysis, and also for the perturbation. And this is supported for most of the solutions that the GPFORCE is supported for, which includes solution 400, 101, 103, for buckling, solution 105, and all the dynamic solutions, which are frequency responses and transient responses. And it's supported for both permanent glued and touching contacts. So here I'm showing you the examples of before and after. So before version 2018, you can see that the totals were not adding up to 0. That's because we did not account separately for the contact forces. But in the new version 2018, we have the force of contact in the GPFORCE output table, and the totals are 0, and it's balanced. So next I'm going to be talking about modules. So what is a module? This is a useful feature that has been added, and it has multiple applications in several industries such as auto and aero. So today's industry requirements call for design of complex structures, as I said, again, a similar concept, that have multiple components, parts, and assemblies, and combining these parts and assemblies can be tedious and cumbersome at cases. So modules are similar to part super elements, however, they don't have any reduction, so that's the benefit. It gives you more capabilities, so you have more control using the module. A module is a standalone section of the Nastran input file, the bulk data section, which typically represents a portion of the structure or a component. So each module is independent and it can represent a component. So here you can see, for example, we have a module for the wing components. We have one for the fuselage, or etc., or we have one for the engines. And these bulk data entries can be combined easily and quickly to manage and to create a full assembly for your analysis, and they can be all run at once. Another benefit of having modules is that you don't have to worry about the duplicate grids. So it is okay to have duplicate grids in every module. So here we can see a section of the input file, the bulk data section, which has the meat of your analysis. The bulk section starts with the begin bulk, and the modules all start with the begin modules. So module 0 entries are optional, and they can go before the first begin module. And you can see here, we have color-coded each module for you. You see how the module 0 can go anywhere in the model, and it doesn't have to be just by itself, as long as it is included under begin bulk. And but in general, to keep track, it's easier to have the entries related to each module separated in your input file, so you can categorize for each module. And then each module will have a begin module and end module. And they have the module IDs, and as I said, the module IDs or the grid IDs don't have to be unique. You can have duplicate grid IDs in different modules. And also, you can use these modules. You don't have to include the whole section of the input file for the module in your main assembly. You can have an include command. So that's another convenient method to make your input files shorter. So also, we have the connecting modules to other modules, the interconnections. MSC Nastran 2018 provides a wide range of flexibility for the user when it comes to connecting and defining connection for these modules. So you can have inner module for coincident connections using the MD bulk entry or MD connect entry. This has several methods for you available, the automatic method or the semi-automatic or the manual. So if you want to have the automatic method, you have to define in the bulk data entries the auto entry in your MD bulk entry in your input file. Then once you have the auto defined, the program will automatically connect the grids from a module to any coincident grid in another module. And again, as I said, you don't have to worry about the duplicate elements. Now, we have other options available for connecting, but the rest are not automatic. So the automatic and semi-automatic options are only available for the inner module coincident connections. You can have flexible connections with the modules, for example, for CFAS or fasteners, for valves, or for DMIGs, and these will be using the MD valve, MD seam, and other entries, as you can see here. You can also have rigid connections for bolts, for MPCs, RBEs, and R joints and R rods. And these are defined using the MD bolts, MDPC, and other entries that you see in the slide. And you can have the contact bodies defined in the inner module connections. So it gives you a lot of flexibility and options to create your assemblies and manage them. And modules are supported in several solution sequences. Solution 101 for contact analysis, including the contact analysis, 103 for normal modes, buckling in 105 for direct and modal complex eigenvalue solutions, as well as modal and direct frequency response and transient analysis types. At the moment, it's not available for the optimization, and it's important to know that you have to use this with the IFP star yes for the new IFP format for input file processing method. So now I'm going to talk about the advancements in the HDF5 result database for this new version. So this release adds more MSC Nastran data types for the HDF5 result database. We have talked about it in previous releases as well, but in this release we're adding more options. And also we're adding more modeling parameters for the user to optionally output data and manage the H5 files. Pattern support has also been enhanced to include more data types. You can see we include fatigue vibration data blocks, or we use solution set outputs, and we have monitor point data in solution 200. We have design optimization and for topometry and topology data that can be sent to the HDF5 results, and a lot of other options that you can see in this slide. Also, the modal matrix for stiffness, mass, and damping are available to output the general matrix data to the HDF5 file. Just like any other methods, the HDF5 also is supported through the assign statement for the user, and you can see here, using the assign statement, you can give it a file. We have also allowed the versioning in case you want to rerun a model. So the HDF5 file will, your H5 file would get a versioning, so it would be like H5.1, H5.2 for rerunning the same analysis or versioning. We have also added multiple modeling parameters to write the model data in a separate file, or you can write the matrix data in a separate file. So this is another convenient method. And as mentioned, pattern support has been enhanced to include the monitor points, design response, and contact forces for HDF5. In this section, I'm going to be talking about the explicit nonlinear dynamics for our solution 700 and the new features. So there has been a change in the solution 700 in MSC Nastran 2018. Before, we used to have LS Dyna portion for our structural portion, and then have a Dytran-based solution 700 for the fluid. And now, because LS Dyna has stopped their contract with MSC and they've decided not to renew their contract with us, so we are utilizing the Dytran technology fully in our solution 700 for MSC Nastran. So for both solutions, for structural or fluid, for both like Eulerian and the Lagrangian, we are using Dytran based. So, and then because of that, we have changed some of our material entries, or some of the entries that were mainly supported in LS Dyna and related to LS Dyna. We have added the capability for the user to use the equivalence options and materials, but using the MSC Nastran entries. For example, for the MAT 1, you will see the isotropic. Or MAT 8 for the orthotropic, and other options for hyperplasticity, for failure, for elastoplasticity. And we have added a new MAT BV entry that I will cover in the next slide. And we have also added new parameters, equivalent MSC Nastran type of parameters for the options that were available for the LS Dyna DI param. and these are switched now to the new parameters. You can refer to the release guide for the Nastran 2018 once you download the solver, or you can also refer to the quick reference guide for more information. So here you can see some examples of the materials, the MAT HE. So we have supported that for the hyperelasticity, but we added additional material MAT VV for bulk viscosity coefficient for the hyperelasticity analysis. And you can see here examples of mapping the old ones with the MAT D entries to the existing MAT 1, MAT EP, and MAT F entries. And if you're running into issues, always feel free to call our technical support team or contact me or Raj, and we will try to answer you and try to find methods for you to convert your existing materials to the new ones.
Just to add to that, we're also creating a manual which would help you switch from your old commands to what the new Nastran standard commands would be for material entries.
Yes, very good point. Thank you so much, Raj. Here are some of the applications that you can see and examples that are done for the Solution 700. We have the shock wave. We support blast wave, JWL explosions, and etc. Here on the right-hand side, you can see a shape charge. A shape charge is a cylindrical shaped projectile. The core is solid and surrounded by explosive material. And you can see that the explosion is toward the center, so it gets superheated and super pressure. So it becomes liquid and shoots out. These are some of the applications for the Solution 700 in the MSC Nastran 2018. I'm going to be also talking about the new features that have been added, automatic coupling surface. In fluid structures, interaction of number of shell segments, you will see that interact with Euler domain. So we have a section where the fluid and the structure sections are trying to interact with each other. The list of these shell segments is called the coupling surface, and it can consist of structure segments, but also has some dummy segments. Before, to simulate these interactions, we use the fast coupling approach, which is often used, and it requires some intermediate techniques and meshing techniques if you have the interaction. But in the fluid structure interaction, these shell segments sometimes go through a hole or a T-joint, and that can, before it created some issues. Now, in the new release, we are adding a user-friendly and versatile approach for running more complex models, and this time it is necessary to use these coupling surfaces differently. So with the fast coupling approach, the surfaces specified the region of the Euler domain, and this region was covered. But so it was acting as a container of the fluid. Now with the new usage, the coupling surface will no longer act as a container of a fluid, but will only act as a barrier to the fluid. And this approach is called the automatic coupling surfaces, and it's available to the users in the new section. So here you can see the T-joint, and you can also see that we have removed the requirement for the closed coupling surface on the left-hand side. As you can see, the section is open and has a hole. And then also in the T-joint section, you can see we also have a hole. We also added some explicit nonlinear materials for subsonic combustion of progression of deflagration. So you can see we added some materials for equation of state for deflagration. These are the subsonic combustion material models to model the firing of bullets and mortars. We have also added noble equation of state to model gases under very high pressure, for which the ideal gas model is less accurate. We have also added enhancements to the JWL equation of state to model afterburning of explosives like TNT and metal oxides. So in this section, I'm going to quickly go over the high performance computing enhancements and features that we have added to the new 2018 Here you see some of the old methods. I'm not going to go over the details so much because I'm sure you guys are interested to see the plots, and we are running a little bit out of time. But before we had some older methods for the MPYAD. MPYAD is the module inside Nastran that takes care of the matrix multiplication and addition and does the matrix solution. And we have added a new method. So totally rewritten the MPYAD to improve and provide better performance. Some performance gain to up to 5 times performance gain can be seen with so many models using the new rewritten MPYAD. So it is important in the features that we have added for the new method. We have added and expanded filtering of matrices to improve the performance. This helps to reduce storage needs and reduce the number of passes, and also increases the likelihood of a dense method, which can have a better performance. So these are all added for your ease of use for the user to have more computationally efficient solution. Here you can see the chart. We have several models that we're comparing, version 2018 in the red versus pre-version 2018 in the red versus the version 2018. And you see how we have gained a lot of performance. So for example, in Model A, we have a solution 111 with P-Bush-T. This was run on a Windows 7 with 8 gigabytes of RAM, and the original elapsed time was about 250 hours in pre-2018, and we have reduced that to about 2 to 3 hours. So you see a significant performance improvement. Another model was Model B. Model B is about 5 times faster. You can see this was a solution 200 for optimization, and it was run on a Red Hat with 6.7 with about 512 gigabytes of RAM using the new ACMS combination with the MPYAD. You can see the performance gain for Model C and Model D. Here we have about 3 to 4 times performance gain. Model D was with interior and exterior fluids. And we can also see Model E. So the Model E did not have that much performance gain. That means that the previous versions had good and useful methods, which did not result in too much. So the new changes did not affect this specific model. So we have also improved the MPYAD for better parallelization. To gain the optimal performance for following model types for equivalent radiant power, ERP models, for solution 103 with many ACED degrees of freedom. For solution 101 with many load cases, this is used for a lot of aerospace applications. This is where you see a lot of gain in performance. And we have added this for solution 111, frequency response, modal frequency response with interior and exterior fluids. It was not very significant for solution 101 with few loads, or solution 144, 146, or for 400 NL static. So here I'm talking about the ACMS method for parallelization with the SMP for shared memory parallelization. You can see some performance gains. So we added a new dynamic scheduling that gives us a better parallelization performance and scalability. Here for the charts, we can see a lot of models that were compared. Here you are interested in the gray part. The gray area is the performance gain for version 2018 with the new ACMS phase 1 that has been enhanced. The model on the left-hand side is 19.3 million degrees of freedom, and it was a solution 111 example, and it has about 600 modes, and it was about 300 forcing frequencies. You can see that we had several improvements using the ACMS for phase 1. And then On the right-hand side, we have a normal mode analysis model of it was a fully solid model powertrain, and this model is also about 200 million degrees of freedom, and you can see the performance gain for ACMS phase 1 in version 2018. And I also want to mention that for the right-hand side model, we were not doing much of outward requests. You can see how this chart highlights the ACMS phase 1. Here we have some examples of ACMS using 16 cores with DMP4 and SMP4 for versions 2018 and versions 2017. You can see the comparison. On the left-hand side, we have an example of a pro-elastic material in a solution 111 model. This is about 20 million degrees of freedom with DMP4 and SMP4. Most of the performance gain for this model was coming from the previously mentioned MPYAD method. So you see that in this, the gray area in the performance gain for 2018. And then also on the right-hand side, we have a very large automotive model, model frequency analysis. This is a very big model, so this is the biggest model that we tried, about 94 or 95 million degrees of freedom, and you can see how performance gain in version 2018 using the new methods, the ACMS methods, has helped for this model. So these are all features that have been added to improve performance. So here again, you can see an example using 16 cores for SMP. This model uses full data recovery, and it's a normal mode analysis of a solder motor powertrain, and it has about 21 or 22 million degrees of freedom and 2,000 number of modes. You can see a comparison between 2018 and 2017 and how ACMS phase 1 helped to improve. Also wanted to mention that restarts have always been available in MSC Nastran. However, we have added the ACMS support for restart from solution 103 to 111 and 112, and this automatic restart enhancement in Nastran 2018 is available now. It has a few limitations, so it depends on the DB-all, so you have to run the model with the SCR node. Since we're running out of time a little bit, I'm not going to put so much emphasis on these, but again, if you have further questions, you can always contact us, contact me or Rod, or if you have technical questions, you can refer to our technical support. Last item that I want to mention is this cool feature that we have added in our solution in our version 2018. It's an automatic solver selection, and it also automatically selects the solver for you and the parallelization method. So it's a very cool feature. What you do is you execute the analysis in Nastran 2018 with solve equal auto, and it will decide what solver to use depending on whether your model is solid-based or shell-dominated, and mostly useful in solution 101 and 400. It decides which solver to use. If you're using a modal or dynamic, it decides which solver to use as well, dependent on your eigenvalue entry that you have defined. And so if you have a solid-dominated model, it tries to use the Cassie solver. But if you have a shell-dominated model, it tries to predict the memory required for Paradiso and tries to use that solver. And this is mainly done in 101 and 400. So if it's started to use Cassie, then it defines what parallelization method is more beneficial, whether it has to use the SMP or DMP, and then it runs the analysis. And with the Paradiso, it tries to decide whether you have enough memory for the Paradiso, and then does the parallel selection. And if the memory is not enough, then again select the parallel processing method based on the available memory. So here you can see we have added some machine learning capabilities, and these will, the program will start to learn more and more based on the available memory. This is an example that we tested. So at first, the memory, available core memory was about 3,250 megabytes. but this was not enough, so Paradiso ran out of core, and the wall time was about 1,796 seconds. Then the second run, based on machine learning, it learned more, and it tried to understand more and better. So you can see here we're a little bit closer, so we get a little bit performance gain, but still we're not running in core. And the third run, as it progressed, is tried to use more memory, and it tried to run Paradiso in core after the training, and you can see that this is when we got the best performance. So again, this automatic solver selection is very useful. You don't have to worry about much, and you don't have to go through different selections. You just define solve equals auto, and you have defined the memory max as well. So depending on the value of memory max, and solve is equal auto will decide what solver to pick for you. You can see the performance gain that we have obtained using this feature. So using the default, which did the serial runs with the default solver, this is the normalized plot that you can see. Then we defined the CPU max set to 20, and this resulted in using the SMP equal to 4. Then we used the solve equals to auto with CPU max equal to 1, and resulted in the CASI solver. And this model was made up of all solid elements. That's why it selected the CASI. And then you can see the best performance was just using solve equal auto without the CPU max specified. And this time it used SMP 8.